Okay, so last time we were talking about Stokes' theorem, and I want to reconceive a little bit. I'm going to flash back first to the fundamental theorem of line integrals, and you'll recall that when we did the fundamental theorem of line integrals, we wrote down both of these kind of right-hand sides, if you will. And the top one kind of came to us first, right? This was, in fact, our change density. Right? And then I pointed out, well, you can rewrite this like that, and this allows us to make a different interpretation of the gradient itself. So you could take the point of view that this is size, and therefore that this is density. Fine, sure, no problem. Right? That's the sort of typical interpretation of size, and density is quantity per unit size. Fine. So, but notice though, this right here, the dx, it isn't exactly what you'd call size, but you could reasonably interpret this as being oriented size, because its magnitude is the size, but it also includes an orientation. It's telling you how this piece of curve is sitting in space, how it's oriented, right? And with that in mind, then this becomes the oriented density. Namely, what you multiply by oriented size to get quantity. Okay, so that was a point of view we took. It seemed a little bit strange at the time, but now here we find ourselves in an analogous situation. So again, Stokes' theorem. We initially wrote the right-hand side like this, and then we noticed we could rewrite it like that. And so again, tempting to say, well, this is size, now area. And therefore, this is a density, previously noted, circulation density. But we can reconceive now, I've already forgotten what colors I used. We can reconceive of the ds vector as being oriented size. Right? Again, the ds vector, its magnitude is the size. Its magnitude is the area of whatever little piece you're looking at. And along those lines, then, the curl ends up being the oriented density. So it's oriented density in the sense that when you multiply by oriented size, you get the quantity. Right? So kind of it's a take, right? It's a certain point of view on how to think about curl. Now, coming back up here, where we were talking about gradient, right? The gradient has both a magnitude and a direction, both of which are natural, both of which mean something. So the magnitude tells us, and in some sense, how much change is happening in the vicinity of where we are. How steep is this hill? No comment on which direction is uphill, right? But just how steep is the hill? And how steep is the hill? A naturally meaningful thing, even if you're not currently walking uphill, right? And then there's the direction that it points. And of course, as previously discussed back in Chapter 2, the direction that the gradient points, that's telling you in which direction that uphillness is actually happening, even if you're not personally walking that way. Okay, so we can make the same interpretations down here now of curl. So curl, again, being a vector, it has a magnitude and it has a direction. The magnitude, perfectly analogous to with gradient, the magnitude tells you how much circulation is happening. How strong is this tornado? No comment on which direction the tornado is oriented, right? But just how much, is this a category 5, a category 3, category 2, whatever. The units are hard to talk about. We're not going to worry about that in this class. But the longer the curl vector is, the more, in some sense, of a rotational aspect there is to the fluid. Yeah, question?
Yeah, so, as opposed to, the greens, which was, 2-dimensional, is this, rotation on 3-dimensional on a 2-dimensional surface?
It's rotation. Don't think about the surface. It's just a rotation of a fluid, maybe like this, maybe like that, maybe like that. There's a lot of different ways that it could be rotated, but it's the rotation of a 3-dimensional fluid. Yeah, absolutely. So, and I'll answer the second part of your question momentarily. So, the magnitude tells you overall how much of a rotation is there. We'll worry about the direction momentarily. And then the direction that it points is telling you around what axis is this fluid rotating. So, in particular, if the fluid's rotating kind of like this, right? Well, then it's rotating around this axis. All right, so to summarize, the curl points in the direction of the axis of rotation, and in some sense that I don't want to be too precise about, its magnitude is telling you kind of how much of a rotation of the fluid is there. So again, longer curl, more rotation, more circulation. Okay. All right, so I like the following couple of scenarios to at least give some satisfaction of the idea that curl, dot product with the curl, would be the thing that would kind of track with the idea of literally trying to find the circulation of the fluid. So what I have here is a picture of a fluid flow drawn twice, exact same fluid flow, two different scenarios of surfaces, but the exact same fluid flow, and so therefore, of course, the exact same curl. Now let's take them one at a time. I am first going to look at a little piece of surface that looks like this. And let's talk about boundary circulation around the boundary of that little piece of surface. Now, as I have it drawn, check it out. The rotation of the fluid is, it's just going right along with the boundary. Right? As we kind of cruise along the boundary here, the fluid is going the same way we are. As we make the turn and come up this way, the fluid is going along with the boundary as well. So you would expect there to be a lot of circulation. Because again, what is circulation? Circulation is a line integral. Line integrals measure the extent to which the fluid is going along the boundary. So a lot of circulation here. So what does the curl vector have to do with this? Notice that the curl vector in this case is pointing in the same direction as the normal vector. And I appeal to your sense of geometry. The fact that the circulation, the fact that the flow of the fluid is in the same direction as the boundary is geometrically tied to the fact that the flow is going around, and the normal vector that the boundary is going around are also pointing in the same direction. Right? So the fact that, let's see here, the fact that we have circulation happening, right, is geometrically tied to these two vectors pointing in the same direction, and therefore this dot product, curl dot in, being large. Now, by contrast, same vector field, different scenario, now a different surface. Looking at this surface here now, oriented in a different way, same amount of surface, let's say, but oriented, just arranged in space now differently. Right? And, well, look, the fluid is kind of doing like this, but the boundary really isn't, right? The boundary's going around a different direction. Right? You wouldn't expect there to be much circulation here. Look at what the field vectors are literally doing. The field vectors at points along in here, kind of like this. And that's not circulation. The vector field is not going along the boundary. So you wouldn't expect there to be much circulation here. And likewise, the rotation of the fluid being sort of out of step with the way the boundary is going is simultaneous with the curl going a different direction from the normal vector. So this not giving you a lot of circulation lines up perfectly with this not giving you much of a dot product. Right, so I think this is geometrically plausible that this dot product, curl.in, tracks with how the fluid is flowing around the boundary. Okay, so that's just intended, again, to be kind of a plausibility check of these claims right here about how to interpret curl, what does it mean geometrically. Okay, yeah.
The fact that the circulation is related to a dot product of the curl and end, does that, can that relate to how we said that work is a line integral?
It's pretty different because work comes from interpreting the vector field as representing forces, and here the vector field is representing a fluid flows. It's just a different context. I wouldn't see much of a connection there. Okay. All right. Okay, so some physical interpretations. I hope these are plausible. Recall when it came to fluid flows, right? We interpreted that if you have a flowing fluid like this, and if there was I like to think of a fall leaf sitting in the water there, well, the fluid flow on this side is stronger than the fluid flow over there. It's like when I don't know if you're ever push a cart at the grocery store. If you just push it on just the right side, it's going to veer left, right? And so likewise, this is being pushed harder on one side than the other, and so it's going to be kind of rotating as you go around. And Green's operator tells you how much. Green's operator is going to be a measure of exactly how much that's happening, right? So the rotation of the fluid, in whatever sense, causes a rotation of the leaf. Okay, so by analogy, curl does kind of the same thing. So this time, now this is three-dimensional, so we have to have a different metaphor. I can't use a leaf kind of floating in space because leaves don't float in space. And so I have to imagine that we have a balloon, little floating balloon here. And, real-world balloons, you have to get just exactly the right amount of helium. Otherwise, they just go right up to the ceiling, right? Or they drop down to the floor. But if there's that perfect amount of helium where they just kind of float in space, and then likewise, another problem. There's that knot, which always hangs low because that's the heaviest part of the balloon, right? And that's going to prevent it from rotating. So we have to imagine a balloon that doesn't have a knot in it. It's a little bit hard to relate to, right? But anyway, hopefully you can imagine a balloon that just doesn't have a knot somehow, and that's uniform and spherical and all that. Okay, that being the case, suppose that your fluid, namely your air, is kind of circulating. It's kind of going around. There's a rotational aspect to the air in some way. There probably is in this room right now, right? The air is coming in at various certain points in weird directions. There's probably a rotational aspect to the air. Well, the curl is a way of measuring what is the nature of that rotational aspect of the air. The rotation of the air, of course, is going to be exactly the thing that causes the balloon to rotate. And so you should expect that the curl will tell you how the balloon is rotating. Because the curl says how the air is rotating, and the air rotating is what makes the balloon rotate. Everybody buy it? So again, the direction of the curl is going to tell you the axis that the balloon is going to be rotating around. And again, it's hard to, I don't want to get into units and how much friction is there between the air and the balloon, and things get weird, and that's not our problem. But in some sense, the longer the curl vector, the more of a rotation of the balloon there's going to be. Totally analogous to leaves with Green's operator. Okay, another physical application. We don't have a lot of time to talk about magnetic fields. It's not really technically part of the course. We don't really have to, but I think it's a really valuable application of Stokes' curl theorem and curl in general. So here's the physical scenario. We're going to talk about, again, a flow of a fluid, this time a flow of charged particles. And this is called a current field, right? So a current field is a vector field representing how charged particles are moving like a fluid through space. Now, you may be accustomed to the idea that charged particles move in a wire, right? And certainly that's an easy way to make charged particles move, right? In that case, magnetic fields just make circles, right, around the wire. Okay, well, yeah, but not all flows of charged particles are inside of wires. In general, when you have a flow in space of charged particles, you're going to get a magnetic field that, again, kind of goes in, well, kind of circular aspect anyway, sort of like that, right-hand rule and all that business. But complicated by the fact that the flow is not in a wire, but it's sort of, in free space. Okay, so here's what you can empirically observe. You can empirically observe that that there is this linear relationship between the current, the total flow of charged particles through a surface, and the magnetic circulation, how much the magnetic field circulates around the boundary of that surface, whatever that surface is. That's just empirical. That's just, they notice it in the lab. Nobody knows why. It just is, right? We wish we understood why. But that, like I say, empirical. Okay, now that said, let's look at this equation right here. Clean up. And when you remove the constants, the mu naught on both sides is just a shared constant. Who cares? Notice the right-hand side is literally just a flux of a flow field, which gives you the total flow rate, which is the definition of current. Number of charged particles per unit time going through your surface. That's literally what current is. Right, so this top line is just an observation that flux is the flow rate concerning charged particles. And we're basically there. This is empirical. Here's Stokes' curl theorem. You see how, again, we've got three sides of the triangle understood now. And as a result, we can conclude that these two integrands are equal, and that tells us that the curl of the magnetic field is the current field, or the vector field representing the flow of charged particles. So kind of neat that these two equations relate. I mean, one is global, one is local, right? This is about the total flow of charged particles through a surface. By contrast, on the right-hand side, we're just talking about the vector field, the flow at a given point. Right? On the left side, we have the total circulation of the magnetic field around the boundary. Here we have just what you might call the circulation density. Right? So, but the thing that connects these, both of these are statements about strong relationships between the movement of charged particles and the behavior of magnetic fields. Right? Both of these say magnetic fields are strongly influenced by the flow of charged particles in their different ways. And the connection between them is Stokes' curl theorem. Right? So if you really want to understand, have a good intuition for why it is that this empirical fact about magnetic fields and currents and stuff, why that can be interpreted as a statement about curl and flow fields, it's because of Stokes' curl theorem. And again, this connection here, the fact that there is this immediate connection between these two purple equations is why we consider these to be morally kind of the same equation. Both of these are Maxwell's fourth equation. Just, sort of different forms, but morally saying the same thing. All right, so when y'all take an E&M class, that's a really important thing to make sure that you're comfortable with. All right. Okay, a real quick fill in the blank. Old news. We've seen this before. Reminder, the idea of a local test. A local test in the two-dimensional case is that if you compute Green's operator and if you get 0, that tells you if your vector field is a gradient, aka if it's path independent, which can be alternatively phrased as closed circulations. Well, circulations, in other words, all being 0. Right? So nice feature, because given a vector field, at a glance, it's kind of hard to just look and see if it's the gradient of something, but it's pretty plug and chug to just crank out Green's operator. It's very algorithmic. Just plug into the formula and then see if you get 0. If you do, good. Okay. And a reminder, the thing that made this work, right, the deep down what was doing the heavy lifting on this is Green's theorem, which connects circulations to a double integral of Green's operator. Right? That's why Green's operator ultimately is the local test. Is because that was the integrand on the right-hand side here of Green's theorem. Okay, everybody hopefully remember this. You may recall as well that I mentioned, if I can get this thing to behave, there we go. I mentioned that we can draw a similar conclusion about 3 dimensions, and I asserted that we can use curl as our local test. I didn't really have the tools necessary to sort of connect the dots at the time, and I mentioned, well, there's another theorem coming, and that other theorem is going to be how we'll connect the dots here. So we now have that other theorem. And the thing that plays the role that Green's theorem did here is Stokes's curl theorem, which relates circulations to flux of the curl. And so the argument proceeds in morally equivalent ways, and in the same way that Green's theorem makes Green's operator the integrand, which makes Green's operator the local test. Likewise, Stokes's theorem has curl as the integrand, which is what makes curl our local test here. Oh, and you know what I can do? I can make that big. There we go. Okay, now that's. There we go. Okay, I can make that bigger now. There we go. So the argument that justifies why Green's operator tells us about path independence in 2 dimensions, morally identical to why curl tells us about path independence in 3 dimensions. Yes?
And does this also show that F is conservative?
Yeah, that's right. Conservative is what it means to be a gradient. Yeah. So yeah, 4th phrasing of the same thing. Yeah, right. Totally. Yeah. Just as a reminder, which I find a combination of hilarious and frustrating: gradient, path independent, irrotational. We got 3 words describing all the same vector fields, and somebody decided we need a 4th one. Conservative means exactly the same thing. Right? I mean, modulo micro regularity issues that we don't want to get bogged down in. Okay, so that's just filling in a blank. Here's a new idea: surface independence. It's a lot like path independence, and for analogy observation purposes, I'm going to remind y'all of the highlights of path independence. Path independence says if you set a boundary, a starting point that you have to stick with, and an ending point that you have to stick with, that's set. It cannot be moved. Sometimes there will be a curve C1 about which you're interested in the line integral, and a curve C2 about which you're also interested in a line integral. And these C1 and C2, if they have the same starting and ending points, for certain special vector fields, very special vector fields. Let's see here, let me do it like this. Very special vector fields called path-independent vector fields. Whenever this comes up, whenever you have two curves with the exact same start, the exact same end, amazingly, these two line integrals will always be equal. And again, I was all dramatic about this when I first introduced it. I think it's shocking that there exist any vector fields that have this outrageous property. They would have to agree for all possible curves that start at that point and end at that point. There's bazillions of them, covering all different points where the vector field has various different. It seems outrageous. Right? Nevertheless, we saw that gradients all work. The fundamental theorem of line integrals is the tool that made that work. Reminder, if you have two curves with the same starting and ending points, you can move around one of them followed by backwards along the other one to make a closed curve that is a boundary. And an alternative phrasing is that closed line integral must always be 0. So again, this is for path-independent vector fields, which most vector fields are not. Right? But path-independent vector fields, these special vector fields that have, take your pick of either one of these properties, surprisingly common in real experience, sort of everyday experience. Okay. All right. So why are we talking about path independence again? Well, there is an analogous idea called surface independence, arguably more important than path independence. There's pros and cons there, but very analogous. The big difference between path independence and surface independence is the dimension. All the dimensions go up by 1. So with path independence, we were talking about one-dimensional curves with boundary points. You might say zero-dimensional boundary points. So one-dimensional things with zero-dimensional boundaries. Here I'm going to be talking about two-dimensional surfaces with one-dimensional boundary curves. Other than the dimensional difference, everything goes very analogously. Suppose we set a boundary so there's a boundary curve. We do have to set that. And now imagine that we have one surface, oriented surface, that has that curve as its boundary, and of which I'm interested in a flux. And then I have a second surface, again, with that same boundary, critical deal. It's got to have the same boundary, and then of which I'm interested in a flux. There are special vector fields called surface independent, where just because of this circumstance, just because of S1 and S2 having the same boundary, that mere fact alone for surface independent vector fields allows you to conclude that those two fluxes are the same. So you see the strong analogy between surface independence and path independence. I mean, they're really, really similar. Shared boundary fluxes must be equal versus shared boundary line integrals must be equal. Very analogous. Here's another observation. Notice that when you have two surfaces with the same boundary curve, kind of like I'm doing with my hands here, two surfaces with the same boundary curve enclose a solid. They make the boundary of a solid. And so this, what you might call S1 minus S2, this oriented difference being the boundary of a solid, being a closed surface, equivalent to green equals blue, is orange equals 0. So the analogies, just off the charts, right? Everything is analogous. Super strong. All right, so this is what surface independence is. Now let me remind you, of course, we talked about path independence, and again, what an outrageous suggestion that anything would ever satisfy this rule. It seems too much. So here we are again. I've claimed that there is a special property called surface independence, and a reasonable position to take would be, yeah, there's no way any vector field would ever, come on, get real, look at all it has to do. This has to work for every pair of surfaces with the same boundary. This has got to work for every closed surface. There's too many of them. How could we arrange the vector field to be just so that all of these closed fluxes would all be zero? Seems outrageous. Okay, so let me finish coloring in the, let's see here, I needed this to be yellow. There we go. Let me try to persuade you that not only is there a surface-independent vector field, there's a whole category of them. Curls. I claim that curls, again, regularity issues, let's not worry about that, but curls are all surface-independent. Now let me demonstrate. For a curl, how would I compute this green flux? Here's the formula for flux. Keep in mind, I'm considering my F being a curl, so this is not just a flux. This is a flux of a curl. Now, remind yourself, where have we heard this phrase, a flux of a curl? Oh yeah, that's one side of Stokes' theorem. Right? So a flux of curl, according to Stokes' theorem, flux of curl is going to be a line integral on that shared boundary. Okay, so what? Now let's look at the blue integral. This blue integral here, let's talk about flux of F through that blue surface. Okay, well again, don't lose sight of the fact that our integrand, again, still a curl. This isn't just a random flux. This is flux of a curl. Flux of a curl is, again, what Stokes' theorem is about. According to Stokes' theorem, this is, again, a line integral on, again, the exact same shared boundary. Right? So because of Stokes' theorem, the green and blue integrals, these two integrals, when the green integral, the blue integral, they're both turned into line integrals around the exact same shared boundary curve, and therefore, of course, they're both equal to the same thing, therefore they're equal to each other. Is that cool? Everybody happy? All right. Wow, that's a lot of stuff, isn't it? Yes.
But could you also relate this to Gauss's triple integral?
Yeah. I'm going to get to that in a minute. Yeah, absolutely. Right. So next question, how would we tell? Right? How can you tell? So we know that there are some vector fields, namely curls. Right? Curls have this wonderful property that they are surface independent, which you can say a couple of different ways. So again, this is, we've already established. How can you tell if a vector field is a curl? And by the way, this is a tricky bit. One thing you could try to do is, given your vector field, which allegedly is a curl, which we hope might be a curl, you could try to find the anti-curl. You may recall, I've never shown you how to find an anti-curl. Turns out it's actually pretty hard algebraically, right? So that's not something we can realistically do. So, okay, back to in practice. How do we know then, right? What use is it to know about some wonderful property called surface independence if you never know when you can use it, right? So, turns out this is where Gauss's theorem kicks in really nicely. Gauss's theorem allows us to turn this statement about closed fluxes, boundary fluxes, into a statement about triple integrals of divergence, because that's what Gauss's theorem says. And so again, we find ourselves in this scenario. Okay, so this vector field, the divergence has triple integral equal to 0 for every possible domain. How could it possibly be that all of these divergences, this divergence for all possible surfaces, for all possible solids, this triple integral is always 0? That's only possible if the divergence itself is 0. Right, so notice it's very, very similar to the argument that we made back here about how Stokes' theorem helps us see that curl is our local test for gradients in 3 dimensions. And likewise, Green's theorem helps us see that Green's operator is our local test for gradients in 2 dimensions. Right? Likewise, divergence, because of Gauss's theorem, divergence is our local test for surface independence in 3 dimensions. And now let's use it. Let's actually solve a problem. Here we go. By the way, this problem would be pretty inconvenient at best without this powerful tool called surface independence. And here we go. Statement of the question. We got a vector field. We have a surface. Compute the flux. All right. Well, let's draw our surface real quick. F is part of this paraboloid, specifically the part above the xy plane. Okay. Now, before we get to surface independence, why don't we just use the divergence theorem here? Tempting. Well, the divergence theorem definitely helps us compute fluxes sometimes, but don't forget, and this is really important asterisk, on all of our accumulation theorems, they all have catch. And the catch for computing fluxes with the divergence theorem is that our domain has to be a boundary. This surface is not a boundary. It's like a bowl that's been turned upside down and the cereal spills out. Right? Does that make sense? It's not closed. This is not a Tupperware. So Gauss's divergence theorem is off the table, and we just cannot apply it directly. It's not going to happen. Now, here's another thing that you could entertain, and this one is not crazy, but it also it is, in fact, kind of impractical. You can look at our integrand and say, hey, if this integrand were a curl, I'd be looking at a flux of a curl, and I could then use Stokes' theorem to rewrite that as a circulation of the anti-curl. And this vector field here actually is a curl. But again, we don't know how to compute anti-curls, right? So this is kind of useless information in some sense. The fact that it has an anti-curl does not help the fact that I don't know how to find the anti-curl. So Stokes' theorem is kind of a loser as well. Does that make sense to everybody? Yes?
So how could you say that it wasn't a curl? Did you...
No, it is a curl. It is a curl. Yeah. And the reason I know it's a curl is because it says so right here, divergence is 0. Okay. And if divergence is 0, that using our theorem here, divergence is 0, then it's a curl. Right? Yeah. But again, I don't know how to find anti-curls. Yeah. So useless. Right? Does not help me. Okay, but surface independence works great. Because, again, per this test up here, if you want to know if your vector field's surface independent, take the divergence. See if you get 0. If you do, yay, surface independence. Knock yourself out, pick whatever new surface you want. You got to preserve that boundary, of course. But, feel free to use surface independence. So, easy price to pay here. We compute the divergence. We get 0. Boom, surface independent. Now we have tremendous power on this problem, right? I am no longer stuck with this curvy, unfriendly surface that the question, gave to us. I can pick any other surface I want. Does that make sense to everybody? Now again, reminder, you do have to keep your boundary, right? So here's the boundary of my original surface, this green surface S. And let's see here, what surface do I want to choose? I like to use the easiest possible surface I can, right? I'm lazy. I don't want to do extra additional work if I don't have to. I want the easiest one I can think of, and I think this nice flat surface in there is going to be the easiest possible surface to choose. For one thing, it's flat. Easy normal vectors. It's either going to be straight up or straight down. That's just a minus sign problem, right? But I mean, I don't have to compute some wacky normal vector function that changes over a curved surface like I have here. Flat means easy normal vectors. Yeah? All right. So, now we have to talk about orientations. Orientations are important. It's a big deal. It's a sophisticated idea. It's essential to get right answers. It's a significant fraction of the ideas of surface independence. So please do pay careful attention to this business on exam questions, when you find them. And let's see, by the way, our original surface, notice it says S is oriented downward. And with that noted, if I could get this thing to, there we go, okay. Our original surface, like so, oriented downward. What orientation do I need on my new surface? Well, here's the rule. Keep in mind, the new surface and the old surface have to have the same boundary. Remember further, boundary is a loaded word. Boundary means something very specific about orientations. So if S and S2, here's my S2 down here. If my original surface and my new surface have to have the same boundary, they have to have the same orientation on that boundary. And so what you have to do, here's the process. What you do is you take your original surface, you play right-hand rule games, you figure out what orientation that given surface puts on your boundary. And then you trial and error with your new surface to see which way will give you the same one. So here we go. Looking at our given, look at our given orientation, our downward orientation like that. And you just got a right hand thumb in the direction, right? And this is ergonomically awkward sometimes, sorry about that. But the thumb in the direction of the given normal. Look at the fingers, right hand only, I emphasize. Right? Your fingers define a swirl. I'm going to say the swirl is kind of like that. And if you drag those swirls down here like so, right? Those swirls. Oh, you know what? That didn't work out very aesthetically, did it? Let me try that again. Those swirls will sideswipe that way. Let's try to make this a little bigger. There we go. So again, thumb in the direction of the normal vector, fingers define a swirl. That swirl sideswipes like so. Okay, yeah.
So are we basically like projecting n onto the
It's not that simple. It would be nice if it were, but it isn't.
Okay.
Yeah. No, I totally know where you're coming from, but yeah, there's some counterexamples, weird counterexamples that sadly doesn't quite work. Yeah. Right. Okay. Now I'm looking at the clock. We're very short on time, and I need to finish this example and say a few other things. So we've got the correct orientation on our boundary now. So next thing I need to do is ask, okay, what about on my new surface? And let's get it wrong first to see what that feels like. Maybe on my new surface, I don't know. Let's try it. Orient it up. See what happens. And if that's the orientation on S2, then right hand, thumb, fingers, swirl, and all that would make the swirl go that way, which side swipes that way, which is wrong. This does not give me the same orientation as what came from the green. So that was wrong. And now let's try to get it right. Let's try now. What if I orient it downward like that? Thumb, right hand, fingers, swirl. The swirl goes like this, which side swipes like this, which is the correct orientation on that shared boundary. So there's our new normal vector, and it is all downhill from here. If I can get this thing to, there we go. You got your normal vector. We were initially asked for flux on the green surface. We cited surface independence to turn that into flux on the blue surface. Normal vector easy, vector field given, easy dot product. This integral is zero by symmetry. X-axis or y-axis, take your pick. And we're done. And we didn't have to parameterize anything. We didn't have to deal with the pullback domain and all the bounds and the square roots and the bounds and oh my gosh, right? Much easier solution. Okay, a couple minutes left. The last thing I want to do is talk about the diagram again, and I'm going to flip over to this page where I've got my typeset diagram. A reminder: this file is in the on the website in the class materials folder, if I remember correctly. Anyway, it's on the website, and just be aware that what this diagram does is it allows you to take many of the theorems that we've seen in this class and reduce them to mere patterns that you can just notice apply in various different places. So, for example, the pattern that we've previously observed about the fundamental theorem of line integrals. When you take a gradient of a function, when you take a boundary of a curve, the evaluations on both sides will be equal. Notice that pattern is the exact same pattern that describes Gauss's divergence theorem, where I take a vector field and look at the divergence of it. I take a solid R and look at the boundary surface of it. Flux on the left, tripling on the right, same answer. So diagrammatically, these two theorems are, morally, structurally the same. And ditto Stokes' theorem. Stokes' theorem as well. If you have a vector field, you look at the curl. If you have a surface and you look at the boundary curve, line integral on the left, flux integral on the right, same thing on both sides. So you don't have three theorems to memorize. You have one pattern to memorize. This diagram is tremendously powerful. It's a huge convenience. Last observation I'm going to make, and then we'll be out of time, I betcha. But there are the special vector fields. You may recall we talked about special vector fields, those which are gradients of something, aka conservative, aka blah, 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 right? Being a gradient, being conservative, being irrotational, namely the curl is zero. Being path independent, namely two curves with the same boundary points will give you the same line integral. Shocking but true that this pattern describing the three different shared properties of these special vector fields there, the same pattern holds for surface independent vector fields. It's just unbelievable. Every curl is surface independent and has divergence equal to zero. Same result. Right? So, neat facts. I think this is a tremendously valuable observation. Again, you don't need to memorize theorems. You need to understand patterns on the diagram. I personally, the way my mind works, this is very, very helpful. I have this long since memorized. And now this is going to sound shocking, but I'm going to encourage you all to memorize this too. And in fact, I'm going to point out, I'll bet you have accidentally memorized most of this already, because there's so many patterns in what we're looking at. Notice that three-dimensional regions, two-dimensional surfaces. Right? The dimension is corresponds to the column. Obviously, what happens when you take the boundary of a three-dimensional region, you get a two-dimensional surface, et cetera, et cetera. And all you really need to memorize is the order that these operations go in. You just have to know what goes where. And with that noted, everything else is just a matter of patterns. And it's, again, just a couple of patterns. Right? So what I'm going to encourage you all to do, stare at this diagram until you feel comfortable. Put it away, take out a clean sheet, try to reproduce the entire diagram. I'll bet you can. And if you can't, then you know what else you need to focus on. Okay, we're out of time. See y'all later. Have a good Monday. See you Wednesday. We will do Chapter 4. Don't forget attendance if I didn't already get you.